Hi everyone, welcome to today's webinar. My name is Melissa Keller and I am a revitalization specialist with the Department of State. Today's presentation will focus on decarbonization of historic structures. And before I turn it over to today's presenters, I just have a couple of housekeeping items. So first thing, today's presentation will be recorded and the recording will be made available on our website at a later date. If you have any questions at all throughout the presentation, please drop those in the chat box and we can save a little time at the end for any questions that you might have. And then with that, I'll turn it over to Michael to introduce the rest of the team.
Thanks, Melissa. Hello, everyone. I am Michael Goodrone with Noresco, and we lead up the team of consultants that provide the decarbonization support for the Downtown Revitalization Initiative and New York Forward programs. I think I probably met some of you attending, but we work together with the various consultants helping to shape the program, and then also offering support for each of you project sponsors and teams. Today we have with us members from Paul A. Castrucci Architects, who are going to share from their experience working with decarbonization and specifically looking at historical buildings as kind of a subset, and share both some theories and implementation strategies, as well as several case studies from some of the projects they've done to highlight potential solutions that you might use in your buildings for DRI and New York Forward. And with that, I will turn it over to Paul and let him introduce himself and each of the members of the team, and then they'll go ahead and continue with the presentation.
Okay, great.
Sorry.
I'll just say hello. Thank you, Michael, Melissa, for the introductions. Sin is going to lead us off.
Great. Hi, everybody. I'm Sin Frost. I'm the marketing manager in all things communications at Paul A. Castrucci Architects. We are a mission-driven and committed. We are a mission-driven firm committed to high-performance, sustainable, equitable, and community-centered architecture. We're based in New York City. I'm joined today by Paul A. Castrucci, principal and founder of the firm with over 30 years of experience in architecture, planning, design across New York State and New Jersey. He's also a pioneer of Passive House in New York City, which we're going to discuss today. And he built the very office in which we work, which is pretty nice. I like it a lot. Gracie Mills is also joining us. She is a senior architect, project manager, urban designer, and educator from Wellington, New Zealand. Gracie has diverse international background in civic, multi-residential, infrastructure, and public realm design. And, maybe when we're done here, you can ask her about that time she was in Lord of the Rings. So let's go ahead and kick it off. Agenda. So today we're going to talk about why we need to decarbonize now. We'll talk through some of what these historic buildings, the challenges and the opportunities that we have to make them more energy efficient, funding cycles, and how to attack these any energy inefficiencies in a strategic way. We will talk through Passive House, which is a framework that our firm has used to meet and exceed New York City and New York State Energy Code compliance. It's one strategy, one path forward, and it might be the best path for your building. So we'll be able to assess that. Case studies we've got, and keys to project success, as well as tools to start tomorrow. So why now? Why decarbonize now? At our firm, we work a lot in affordable housing, so we hold some truths to be evident. We are experiencing a housing and climate crisis. There's shrinking affordability across New York City and state. There's a loss of rent-regulated units, a growing population, which means less affordable housing across the board. And new construction alone can't solve this crisis. We need to utilize the buildings that we have. Many of them are, aging and carbon-intensive buildings. So how do we find some solves to make those buildings more efficient and improve that building stock? It's estimated that over 90% of buildings currently standing in New York State will be standing in 2050. So we've got a lot of work to do. And then a couple of numbers that you might already be aware of. New York's 6 million buildings are responsible for 30% of statewide greenhouse gas emissions. And here in New York City, that's 68%. So we've seen the ramifications of this. We've seen flooding, we can feel the heat, and then maybe our neighbors or our friends are experiencing health risks as a result of it. So it can't wait. And swapping, energy, swapping gas emissions is more gas emissions heavy systems like gas boilers, et cetera, with electric systems can help, but it can be expensive. So we'll talk about how to do decarbonize in a more cost-effective way. Typical historic building characteristics. Maybe you're confronted with one or a few of these that make it feel difficult to decarbonize your building, but there is hope. We've been there, and we're going to talk through a few energy conservation measures that will help you enhance the energy efficiency of your building. Responsive energy conservation strategies. So we'll talk through these with our case studies, but envelope upgrades can help insulate, electrification of heating and cooling, ventilation, and so forth. On-site renewables, I think everyone's heard of solar, everyone's heard of geothermal. We're really excited at our firm about on-site wastewater heat recovery, which is a system that captures warmth from used water like showers and drains to preheat fresh water that will enter the building, and that will save money and energy for your building. Oh, and I'll pass it off to Gracie.
Thanks, Sin. So when we're thinking through our retrofit case studies, which we'll talk through, we like to organize them in sort of two types of projects. The first one is substantial rehabilitation or gut rehabilitation, and that's actually most of the case studies we're going to share. Everyone's obviously familiar with this type of work, but essentially it's about doing all of the upgrades at once. So that would be the envelope and all of any kind of mechanical systems that are being upgraded or retrofitted. That would all happen at one time. And of course, this generally means the building is going to be vacant during construction, since it's going to be a significant amount of work that's happening all at once. By comparison, we also have some projects which we call a phased approach, and this would be in buildings where, for example, tenants are going to remain in place during the work. The difference here is that we will often think about replacing components or upgrading systems incrementally. So a good example of this is we might decide to tackle the envelope upgrades first, improve the facade, replace the windows, add insulation, that kind of thing, before we upgrade the systems. And the reason for this is that, there's no point in installing more efficient mechanical systems if we're just going to lose all of the heat through an uninsulated facade, for example. The other thing about a phased approach is that it means that the improvements to the building can be aligned with budget and incentives that are available. So this can often be something that can be, planned out over a number of years, and upgrades can be carried out according to the funding cycles. Important to note that for both of these approaches, we generally find that an energy model and energy master plan is critical to be able to figure out, the appropriate solutions and the appropriate phasing for those solutions. Next slide, thanks. So when it comes to kind of assigning some of these energy conservation measures that Sin walked through, we want to be aware of the specific needs of the building you're working with and also the funding cycles. So we wanted to call out 4 pieces of this that we think are really critical. The first one is looking at understanding the mechanical systems lifespans. So, if we have a mechanical system that's been installed in the last 10 years, for example, it probably doesn't make a lot of sense to be replacing that immediately, but maybe we, again, tackle the envelope first and then plan for a mechanical system upgrade or replacement at the time when that ages out. Secondly, historic preservation limitations. A lot of the case studies we're going to talk through, and probably many of your projects are dealing with this. It's important to understand how these restrictions can be dealt with in combination with the energy conservation measures, and that often requires kind of creativity in the approach and some flexibility in how we apply the energy conservation measures while also keeping the character of the building and the facades. Thirdly, being aware of the incentives and tax credits that are available for the project. We often find this really helps determine and guide the right decisions for the project. So the whole team being aware of what's available and understanding what type of upgrades this supports can be really helpful for determining the right strategies for the project. And then lastly, being aware of the occupancy and use status of the building, which will help us determine if a remain in place retrofit is going to happen, or if the building will be vacated and work will happen all at once, and then tenants will move in. Next slide. So as Sin mentioned, our firm is particularly focused on passive house as a framework for decarbonisation. We really like using passive house because we find it to be a very holistic and flexible approach. I think the main thing to know about passive house is that it's based on a maximum energy per square footage parameter. And that basically means that there's not a specific prescribed design solution. You can kind of vary a number of factors that can include envelope, insulation, air barrier, mechanical systems, as long as you arrive at that maximum energy use per square foot. And so again, especially in the context of historic preservation, we think that it's a really flexible approach, and being holistic really helps us find the right solution for each unique building that we're dealing with. Just quickly, the main principles are to reduce heat loss and gain. So again, that goes back to thinking, the envelope is the first line of defense. That allows us to reduce the energy consumption, the heating and cooling loads and the loss through the facade. And then in so doing, we also are able to actually really improve the health and comfort for occupants. I'll hand it over to Paul for the next slide.
Okay, thank you, Gracie. So again, passive house framework. It's parallel to the decarbonization process. Many of the same energy saving measures. So passive house starts with the building envelope, air tightness, continuous insulation, thermal bridge-free construction, high performance windows. So when you're looking at a passive house, you're looking at every corner, every connection to the building, in every direction that you have your continuous insulation, that your airtight levels meet from your wall to your roof, to your floor, to your ceiling, to the cellar, that there's no breaks in air tightness, continuous insulation, and that your insulation is connected to your windows. And then again, you're taping your windows, or you're sealing your windows so there's no air leakage. Air leakage is a huge contribution to energy loss, because in these old tenements or old row houses, 50% of the energy is lost through heat rising through your building and then leaking out the openings in the upper portion of the building. It's important to consider the building envelope. You have to think of it as like a bucket filled with water, and every time you miss a thermal break, every time there's a piece of insulation that's missing, it's water leaking out the bucket. And the more holes you have in your bucket, the least you're going to meet your goals. So with passive house, you're taught, and there's diagrams and teachings and learnings that you're going to look at every different conditions. You're drawing a line around the building envelope. Then we're going to use the energy recovery ventilation system. You're going to be able to reduce the size of your HVA systems, a big savings in energy if you're reducing your energy. And then most important, there's quality control, testing, and certifications. Many of these items are now in the building code, building energy codes. Passive house is a little more stringent, but it's the same principles, and it's just important to follow them. Okay, next slide. And we do encourage people to take a passive house course, take a good carbonization course, and try to look at your projects in a holistic way. Why passive house? Which is the same thing as why decarbonization. Health and comfort with a passive house or with a building with energy recovery ventilation, you bring in continuous fresh air into the apartments, into the building that's being used. Critical after COVID, more healthy in the winters, and it's a more comfortable environment. You often have triple glazed windows, so when you're standing next to the windows or openings, it's a warmer area. passive house decarbonization is affordable. You will increase your cost of construction, but at the same time, you're reducing energy uses, which is savings on your utility bills, and you're reducing sizes of mechanical equipment. We do enjoy passive house because it is proven. Our energy models are meeting some of our benchmarking models. Its passive house energy model has been used for well over 20 years, and it keeps being improved from field experiences. And then again, working with passive house and decarbonization, we're always trying to align our goals with the preservation of our historic structures. Next. Passive house standards, new construction versus retrofit. New construction is pretty straightforward. You have the opportunities and the ease of generally insulating from the exterior of the building, air sealing from the exterior of the building in most cases, which makes everything easy. There's no structure in the way, as you'll see in some of the details as we go through our case studies. New construction is a little bit easier. It's a little more stringent in terms of air infiltration, but EnerFit, passive house, which is the rehabilitation of buildings done to passive house certification, is tailored more towards historic structures and existing structures. So it's a little more forgiving in thermal breaks and air tightness of a building. Next. Okay, this is 158 Clifton Place. It's a 4,000 square foot two-family residence. The building was constructed just after the Civil War, around 1870, 1880. The condition of the building, it was in poor condition. All systems were not functioning. Every exterior element was well worn, past its age, or missing. Next slide. This is the tax photo from the 1950s. So there's a wood frame structure, had wood cladding. All systems were in poor condition. Next image. So this is kind of a great project because we had a really good client. The client is Sorkill Lumber. He's a recycler of woods from buildings being demolished throughout the Northeast. So we had every piece of wood in this project was recycled, probably except for the plywoods. So at the front facade, we took a more historic approach, used a Shukoban cladding, which when during the process, it's burning the wood, but it's protected at the same time, it protects it against the elements, which is a very traditional method. And then we met a lot of the historic characteristics and trim in the building on the front facade. Whereas the rear facade, we took a little more liberal approach and had a modern approach to our facade, again, with recycled woods and strips of wood. Both systems are a rain screen mineral wool insulated system. There's a rooftop solar system, which provides enough electrical power for the heating and cooling for the entire building, plus a little bit more. It does not account for all the flood loads or hot water, but it's a good portion of the building. Let's see, next slide. So here, building sections of the building. Again, we're illustrating all the conditions that you come across from roof to lower floor slab and air barriers. Next. So here at the roof, we have our roof insulation meeting our continuous insulation at the front of the facade. It's a wood frame structure. So we have 3 inches of mineral wool on the exterior, on the front walls and rear wall. And then between the wood studs, we're filling that cavity with blown in cellulose. Our air barrier is both on the inside and at the outside of the building. The outside is air barrier and moisture barrier. Inside is just principally an air barrier, and they're generally vapor open. Next, please. Here at the floor condition, which is sometimes a tricky situation when you have masonry buildings, this is wood frame. We have continuous insulation with no thermal breaks. Next slide, please. Again, this is where the first floor is meeting the lowest level. The first floor is brick construction in poor condition. The brick was restored. It had a stucco finish, so we put an ephes, 3 inches of an ephes finish in front to match the historic character of the building. Again, here where the cellar is an unconditioned space, and that our air barrier is stopping at the first floor, and then our insulation level is between the joist blown in cellulose and then 2 inches below the blown in joist. Again, here we're illustrating continuous insulation meeting the windows in plan at the roof details and at the roof mansard roof. We have a significant amount of insulation, a little bit of wood as a thermal break, but one, it's a wood material, and two, there's a significant amount of insulation to stop any loss of energy here. And again, these conditions are energy modeled, which is a requirement in some codes, and to measure how much energy loss, and we try to minimize, all thermal breaks are minimizing the energy loss at these conditions. Next slide, please. All right, this is another curious project in Yonkers, New York. Another adaptive reuse of a warehouse built at the turn of the century. It was for the Ford Motor Company. It was a storage facility for in the local area for Ford Model Ts. This is a live-work situation for 2 artists, David and Chie Hammonds. It's a significant space. So they have a lot of storage areas and a lot of places to exhibit their work, as well as their workshops. In this case, we've they had their interest was not covering the exterior facade with insulation. It wasn't a historic structure, but they wanted to keep the texture of the industrial building, the texture of the brick and the stone, and so all the brick was pointed. Masonry was repaired and such. The building had some deficiencies to bring it for an adaptive reuse for the proposed use of exhibition and workshop space. So while there was natural light at the perimeter, there were many spaces that were deep and with no natural light. The building was principally uninsulated, and as you see in the slides, we were bringing in natural light through skylights and openings in the center of the building. Some of the ceiling heights in this space were low, approximately 12 feet, which was not adequate for their use. So there's a whole section of the building where we raised the ceiling to 20 feet and then incorporated a series of sawtooth skylights. And that does 2 things. It brings in the north soft light for the artist to work and exhibit their work. And then on the sloping side that's facing south, we took the opportunity to put solar panels. This project has a 40 kilowatt solar panel system, and this covers more than the heating cooling requirements of the building, but not quite net zero. Here's our exterior wall construction, and with masonry structures, we have to take a little greater care, do our research, look at our building science, and doing some energy models. Traditional masonry historic structures, the masonry was not in the freeze thaw cycle as much because the buildings were heated from the inside. There was no insulation to keep for the heat, and the heat was absorbed into the thermal mass and then released to the outside. So there's a great loss, but the masonry was warmer. Here, where we're insulating, we're increasing the freeze thaw cycle, and we do not want to make a significant difference to that because it damages and may damage the brick or the masonry. So building science and energy calculations determine that this is a reasonable approach where we put 4 to 5 inches of mineral wool insulation on the inside with the air barrier on the inside, still keeping the building is less than the freeze thaw cycle, but it is increased. We've been doing this for over 20 years, and we're finding that there's no damage to the brick structures we've been working on. Next slide, please. Here again, the roof, continuous insulation over the roof, over the existing wood joists. We did have some new bulkheads on this building. We did use metal joists. We had 6-inch continuous insulation. We thought we'd see, did it make any sense to add any more insulation? This is the early design detail where we show insulation between the metal studs. In our energy modeling and our building science, we've found out that insulation between metal studs is you're not getting the full value of the insulation. It's reduced by 30 to 40%, and that does not make financial sense. So typically our early projects, as we did and study this, we eliminated the insulation between studs and kept continuous insulation wherever it was possible. Next slide, please. This is a typical detail that you see for a roof drain. You might find it in a historic structure or new building. Similar issues, the roof drain will either be cast iron or PVC. There's still a thermal break in the materials. So in order for us to adjust this, make this thermal break better, we're insulating a minimum of 15 feet in the vertical condition of the pipe, and then fully in the horizontal position. This stops our thermal break and our energy loss. And 2, it stops the condensation. So condensation will form if the pipe is not insulated. If it's horizontal, there'll be more dripping onto the floor or more dripping onto a finished ceiling, and you'll see a lot of stains. So this is our solution. Next slide, please. This is a great project. This is in Harlem, New York. This project received the NYCHA, no, I'm sorry, not NYCHA. NYSERDA Building Excellence Award Early Design Study, as well as the demonstration Building of Excellence. This is a 2-part project. The front part of the project is a former school, which is typical construction you find out through the Northeast, large windows, masonry structure. Here we're adding a floor to the building, greenhouses and meeting rooms. And then behind this, there was a former parking lot, and on the parking lot, we're building new housing. Next slide, please. Again, this facade, you can see that there's a lot of large brick masonry openings for windows in the structure, brings in a lot of great air, but there's a significant loss here. Project is also in the flood zone, so we had some challenges here, as you'll see in the next slides. We did bring the entrance stairs down to the floodplain to meet the building regulations and codes. Next slide, please. This is the uses on the upper floors, a multi-purpose room, gymnasium, and meeting space for the community, and then a food justice campaign greenhouse, an educational center, and this was all part of working with the community, and this was partnership with the local public high school across the street. Next slide, please. This is a cross section to the our exterior wall. Starting at the bottom here, the client, this is the cellar space. The cellar space is 3/4 of it is in the floodplain, design flood elevation. So we need to flood proof here. The client decided, along with the team, to dry flood proof the cellar. So this cellar space would be usable. So we need to keep the floodwaters out in times of emergency. So we have a mats concrete slab over the existing concrete slab, and that's anchored down into the soil with piles and rock anchors. So there's no uplift because there's a tremendous amount of pressure from hydraulic static when there is a flood. And then the exterior walls, again, to keep the floodwaters in, there's a new concrete wall poured, again, to keep the flood waters out. There's waterproof membrane and an insulation membrane continuous at this location, most for air sealing and for insulation purposes, as well as keeping the floodwaters out. This building with the large windows, we're in the process of energy modeling, and the initial results are saying that the windows should be a triple pane to meet the Passive House standard for energy reduction. But we're also looking at the thermal breaks at each floor. This is not a wood frame structure, so we're not able to manipulate the structure. So there's less of a thermal break here. This is concrete and steel beams. So we're finding that the windows are a greater thermal break or a greater source of energy loss than the floor construction. So our focus will probably be on the windows, going to a triple pane, but we might also need to try to make the transition from the floor, the exterior through the floor to the interior better, while we might be insulating for the maybe 2 or 3 feet to the inside under the slab and structural steel there. So this is in process, and we're looking forward to seeing what our final solution to this puzzle will be. Next slide, please. Okay, again, air and moisture barriers are continuous on the interior of the building as well as the insulation. And I guess we spoke about the triple glazed windows. Next slide, please. This is another condition at the perimeter of a roof. This is showing new construction, but it would be similar for existing construction when we do have to tie our roof to our facade. Here, this is a roof bulkhead, new roof bulkhead on this structure. We need some blocking, wood blocking or some sort of blocking to connect our exterior metal flashing to the inside. Here we're showing it with wood. We're doing energy models to see how much bulkhead we have, and is wood a good enough thermal break, or do we need to do better? Doing better would be a compressed insulation product that provides a thermal break that gives us an R2 or 3, better than wood, and that's nailable and that we can fasten things through to it. So again, this is depending on the amount of blocking we're required to have here and the lengths we're calculating to see what's the most effective way to reach a passive house standard, which will bring us into a minimal energy use. Next slide, please. Okay, this is Gracie will take us on to this next project.
Thanks, Paul. Okay, so this is a project of quite a different nature to the ones we've talked through so far. It's a 3-building energy retrofit, and it's actually in the design phase right now, so very much early on. You can see the 3 different building sizes here, spanning from around 37 to 78,000 square feet, and we received a Empire NYSERDA grant to look at energy efficiency measures for this project. A couple of notable things about this, I would say. One is that the tenants are going to remain in place, unlike the previous projects, and so we're really thinking through how we can implement these measures while working around that constraint. And the second piece is that we have, part of the grant is to actually do a facade overclad. That means that the existing facade is not historically protected, but it also means that we have an opportunity to think through a solution that can be used here, but it can also be replicable for the many other buildings around the state that are subject to similar conditions. Worth noting that the buildings are not particularly old. One of them is as recent as 2008. Next page, please. So the existing conditions we have are the flat brick facades that we were mentioning, no fire escapes on these buildings. All of them have central gas-fired boilers with a hydronic baseboard heating system, which we're going to retrofit. We'll talk through some of those approaches. All of the buildings also have through-wall AC sleeves in every bedroom and living room, and that's obviously subject to the air leakage that we see with those units. We also have central gas-fired domestic hot water system in these buildings, and then we have a central exhaust ventilation system, which we are looking at how we can retrofit that and introduce an ERV as part of that system. Next slide. So some of the solutions we're looking at here, we already mentioned the overcladding solution. We are studying the potential of doing a modular facade system here, but again, the replicability is going to be really important. We're also proposing to replace the gas-fired boilers with a heat pump, but importantly, we want to reuse the existing hydronic piping for that system, and actually that will now become a heating and cooling system instead of just heating. And that's going to allow us to actually remove the AC sleeves in those locations, which obviously helps again with air leakage and heat loss. In addition, we're going to switch out the gas-fired domestic hot water for a heat pump system, so part of the move towards electrification and removing fossil fuels from the project. We mentioned already the central exhaust ventilation. We are proposing to retrofit that with ERVs, and in that case, we'll try and use the existing shafts where we can, but doing the overcladding gives us a nice opportunity to actually run new supply ducts between the existing facade and the new facade. So that's something that's enabled by doing the overclad. And then lastly, we have some outdoor space in one of the buildings where we're going to be installing geothermal wells, which will provide a huge amount of the energy needed for heating and cooling in the building. Okay, next project is a tenement retrofit, multifamily residence around 12,500 square feet. This project, if you go to the next slide, this project did, we were required to preserve the historic facade, which has a lot of character, as you can see. But other than that, it was a pretty substantial rehabilitation of the building. It was a six-story building with a cellar, pre-1900, and when we started on the project, hadn't had upgrades in around 50 years, so the systems were basically all inoperable. The building wasn't insulated, and in addition, the project's in the flood zone, which adds additional complications to the lower floors. Next slide. So, the main part of the work here was preserving the historic facade, as we said. But beyond that, we actually replaced all of the floor joists in the building, and then some of those passive house principles we've talked about earlier, the continuous air barrier, continuous insulation, reducing thermal bridging throughout, looking at a passive house energy modeling approach to determine the best outcomes, and then other mechanical pieces like relocating boilers to the roof out of the flood zone area. And this project's now complete, and what we're finding through the benchmarking is that it's performing within the 95th percentile of comparative buildings, which is, really points to the effectiveness of this holistic kind of passive house methodology that we've been using. Next slide. So a couple of drawings and details from it. One of the interesting pieces about this is a lot of what we find in a lot of these tenement buildings is that the central circulation stairwell is really tight and there's no space to be adding insulation in the stairwell. So what we ended up doing and what we often see is that the stairwell actually has to be excluded from the thermal envelope, becomes an unconditioned space. So you can see in this diagram here, that the envelope is actually designed around that existing stairwell. In terms of the details, this is similar to some of the earlier masonry structures that we shared before. I think one interesting piece to note here is that, again, the insulation and the air barrier on the inside of the masonry, but you can see that in order to have the insulation be as continuous as possible, we're able to set back the floor joist from the masonry, and so the insulation could run behind it, and then you have to have a little bit of fire stopping, which does cause a thermal bridge, but it's pretty minor, a pretty minor thermal bridge compared to what we see with, for example, a concrete structure. And again, thinking through what the appropriate amount of insulation is relative to the freeze-thaw cycles of the existing brick was important here. Next slide. So similarly, the challenging areas often tend to be where the floors meet the wall and kind of at the structural supports. So we come up with different solutions based on each unique condition. In this case, again, we had some thermal bridging occurring at the structural connections, but what we were able to do through energy modeling is to expand the insulation 2 feet between the floor joists away from the masonry, and that actually really helped to mitigate the thermal bridge in this scenario. So the insulation can be as continuous as possible. Next slide. Okay, our last project here is another affordable housing building. In this case, it is requires SHPO approval, so the facade had to be preserved as is. And one of the main solutions we want to talk about here is that we proposed a unitized heat pump solution that would be, in each bedroom and living room of the project. And the driving factor behind this is that we're really interested in how we can be reducing refrigerant in projects of this nature, which a unitized system obviously helps with that. Especially, there's a lot of regulatory changes happening around refrigerant, and this came at a moment when this seemed like a suitable way to tackle that challenge. So again, here we had residents in place that we're planning around, and an constrained budget, being an affordable housing project. Next slide. So this was yet another project that was completely uninsulated when we came to it. It's a cavity wall system, and again, we're doing insulation and air barrier from the inside. So it's that double, we have a liquid applied air barrier against the masonry, and then a secondary sheet vapor barrier on the interior. And for this project, we actually conducted what we call a hygrothermal analysis to determine exactly how to deal with the condensation issues and the appropriate air barrier for this existing wall. And we came up with the system that you're seeing here. Next slide. This is just showing that unitized heat pump solution. This was actually the first time a kind of facade louver like this has been approved by SHPO. And we, as always, we really need to detail these penetrations to minimize air leakage and thermal bridging. Of course, there's going to be some inevitably, but this was a really tight solution that kind of best outcome for those challenges. Next slide, I'll hand it off to, one more. So last detail, this is a window head and sill. Similar to some of the earlier details, of course, we're looking at how to provide continuity between the insulation and the window head and sill, and working with the existing masonry structure to minimize impact on the historic character. And I'll hand it off to Paul.
Okay, thank you, Gracie. So we've been working on passive house and decarbonization for a number of years. These are some of the things that we find that really help a project, keep a project on budget and built the way we originally designed it. So bringing on a general contractor, construction manager at the onset of the project to help keep us on budget, review details, make certain it's buildable, and that we all understand the project and we're finding the most economical solution to carry forward so things aren't VE'd at the end. It's important to identify the historic preservation strategy for the project. There's many different paths, there's many different solutions. It's an issue, but there's solutions. So if you identify them early and find solutions for them, you'll be able to maintain them better throughout the project. Energy modeling, energy audits are all important. So you have an energy master plan, how the project's moving forward, and you set your goals to how energy efficient you'll be above the code, or whether you'll meet a passive house standard, which is a little bit more stringent, which stipulates how much energy we'll use per square foot of building. It's important to analyze and understand the thermal breaks in the building and how they affect the energy use and energy loss of the building. Air and moisture barriers are critical. As Gracie mentioned, sometimes when we're uncertain of the base, when we're doing our initial thermal analysis of thermal breaks, if we don't have significant information, we might have to do a hygrothermal, which is a more precise understanding of the thermal break. And if you're seeing that there's the temperatures aren't right as they transfer through the wall, and you're going to get, and there's cold air that's going to meet some of the warmer air on the inside, you're going to get condensation and mold, and that's something you do not want on your project. So it's important to know when to study these issues. During construction, pre-construction, we find doing mock-ups of, which we're doing in this image, of bringing the insulation, bringing the window together. All the exterior envelope components are being are put in place so the contractor knows how he will perform through all the conditions and identify if there's any easier way or more effective way of carrying out these details. It's a very useful learning tool. Next slide, please. Again, cost analysis, continuous cost analysis throughout the project to know that you're going to be on budget and that the energy saving measures you're taking will have some payback. period of time. And typically it's reasonable, but we do look at all issues. Understanding the life cycle of a building, especially in historic, you may be looking to save, if the boiler's 20 years old, you may be looking to save the distribution system, as Gracie mentioned in another project. That's a huge cost savings if you can take a portion of that old system and adapt it to a heat pump systems. There's more and more different types of heat pump systems available to provide better solutions for dealing with our historic structures. Integrated design, we always try to have a really good team. We meet with our clients, we meet with MEP engineers and consultants, so we all understand the energy issues when we're designing for our buildings. Commissioning and inspections during the construction period. It's important that the contractor carry out everything as per your details, that somebody is looking to see that the insulation is continuous, that the air barrier is continuous, and then again, that it's being tested by a blower door test, which is the basis of Passive House, but it's also in many of the new building codes in certain systems. So we're finding that the local building codes, New York State Building Code, New York City Building Code, are coming up to a Passive House standard and carrying out some of the same standards in terms of ensuring that the work be done. And at the end of the project benchmarking, it's good to understand how your building performs after you've completed it. Did it meet the model? And does it continue to meet the model? And if it isn't, maybe there's some additional commissioning that needs to be done, or mechanical equipment that needs to be adjusted. Next slide, please.
Thank you, Paul. So finally, to round out, there are so many tools online to be able to access to decarbonize your building. We are very fond of Building Energy Exchange. They're based here in New York City, and they have a ton of resources. So I don't know how to share it in this chat, but I'll try to find a way to get that information to y'all. But they have retrofit playbooks that are great for 1 to 3 stories, so smaller builds, as well as pre-war and post-war, a little bit larger builds. There are a few NYSERDA flagship programs that are available, so cost shares for energy studies, tax credits for your retrofits, and obviously solar incentives. So I highly recommend you consult those programs as well. I will also share that link. And then Con Ed, they have a few generous incentive programs. So you're not, it can be overwhelming to see all that your building needs to achieve in order to decarbonize, but there are ways forward, and NYSERDA and all of these programs are here to kind of help ease you into that. And of course, Downtown Revitalization Initiative and New York Forward have these compliance paths, and they have a ton of information on their website as well. And there are 3 options for compliance pathways. You can meet the New York State Stretch Energy Code, obtain the Energy Star score of 90 or better, or 3, obtain a certification from an approved third-party organization. So, we've gone with FIAS in the past, but there are many ways to ensure that you are building and decarbonizing in a holistic way. And you can find out what path might be best for your building. Thank you so much for taking the time to hear us out today. We're here for any questions. I'll also drop our contact info in addition to NORESCO's contact info. Thank you, NORESCO, and Downtown Revitalization Initiative and New York Forward for having us today.
Wonderful. Thank you guys so much for the presentation. I'm not seeing any questions in the chat just yet. Maybe we could just give folks a few seconds to put any questions in if they have those. All right. Not seeing any questions. So thank you guys so much for the great presentation, and we'll have this posted on our website soon. Thank you.
Okay, thank you all. Take care.